Greetings and welcome to my new calculus channel. Again, my name is John Gabriel. So in the past couple of videos, I've been talking about the so-called calculus of Newton and Leibniz, and I've been telling you how they did not really know what they were doing because they couldn't explain why they were doing what they did. So, for example, Newton would call his function the fluxion, and he'd call the actual function itself, which contained the so-called independent variable, he'd call that the fluent. So what Bishop Berkeley said was that this particular method that Newton used, and you can find a copy of the original at this link, and of course the actual document is a lot better than looking at the original. So what it says is that now the other method of obtaining a rule to finding the fluxion of any power is as follows: let the quantity x flow uniformly so whatever that means, and be proposed to find the fluxion of x to the n. Now the fluxion is the derivative of x to the n, right? Whereas x to the n is called the fluent. In the same time that x by flowing, whatever the heck that means, becomes x plus 0. So you can clearly see that Newton didn't know what he was doing. Okay, he was basically just making up stories, the same as Leibniz. They didn't understand why the calculus works. So they said the power x to the n becomes this binomial, okay? That is, by the method of infinite series, this expression and the increments O and these increments are to one another as 1 to this. So what does that mean? Okay, that's actually not too difficult. All he's saying there is this. He's saying that that if we divide this expression and this expression by O, then we'll have 1 and this expression here, right? Because the O's cancel out, okay, and so on. So this is to this as this is to this. So he's talking about proportions there, which is, by the way, not even relevant, to be honest, because it really has nothing to do with the argument. And then he says, let now the increments vanish and the last proportion will be 1 to n to the x. In other words, let all these increments here vanish. All right. So then he says that he calls these actually ghosts of departed quantities. Now, it's quite hilarious because neither Newton nor Leibniz could explain why their calculus worked. And this is just for the derivative, by the way. It turns out that when they tried to explain the integral, matters were a lot worse. In other words, the summation. My historic geometric theorem takes a very same example that you see over here. And if we go and look at it in more detail, what does it say? It says the same thing, really, doesn't it? Because if we just let the h be an O like that, and then replace all the h's with O, we end up with what Newton had. But it's perfectly okay to discard all these terms that have an h in them, right? So these terms here can be discarded. Why? Because they're equal to the difference, which is q of x comma h. Now, some functions, it's much harder to see what this expression is. Okay, it's much more difficult than just a polynomial, but it's always true. It's always the case that you can toss away all the terms that have a factor of h in them, and anything that remains in x or a constant is in fact the derivative. Okay? So I was the first to explain this. Unfortunately, it's not true that Cauchy rigorized calculus. He didn't, as I explained to you in the previous videos. I was the first to produce a rigorous formulation in human history, and possibly more advanced civilizations have realized these facts already. Alien civilizations, that is. Now remember, my historic geometric theorem is not the new calculus, okay? So this theorem over here is not the new, it's realized from the new calculus. Well, what's the difference in the new calculus? Well, I'll tell you very quickly what the difference is. So while you have this in mainstream calculus, the new calculus looks like this. It says x plus n minus fx minus m all over m plus n is equal to f prime of x plus q of x m n. And by the way, these m and n are very well defined. If you have a curve like that and a tangent line, m and n are the distances to a parallel secant. Okay, so that's all that m and n are. And of course, this expression here is always equal to 0, and it's called the auxiliary equation. It doesn't help you setting this to 0 in mainstream calculus because you don't get an auxiliary equation. You get just a bunch of garbage because it's based on a non-parallel secant line, which is this expression, whereas this here is based on a parallel secant line and uses the mean value theorem. Okay, so that's pretty much it for now. I don't think I have anything else to say. Become a subscriber if you're not one already. Tell your friends about it and contribute to my efforts to spread this knowledge at a link that I'll place in the details section of this video. So until next time, my name is John Gabriel, and this is the New Calculus channel.